All right, we're good. Okay. So last couple things we need to talk about are some other properties of the dot product. Most of these are pretty obvious. It's going to look like a lot of multiplication properties that you've seen in the past. Like if I change the order, it means the same thing. So we say that that's commutative, right? I can do u dot v or I can do v dot u, but I end up getting the same answer either way. So order of dot product does not matter. We also can distribute a dot product through like you would multiplication. So that's what the second one is. So if I have u dot product with two vectors that are added or subtracted, I would just do u dot v or v dot u, either way, and then u dot w, and then add those together, whatever those are. The third one says if I have the zero vector, which is the vector 0, 0, and I take a dot product of that with any other vector, I just get 0. That should make sense because everything is just 0. I'll hop down to the fifth one. The fifth one is the associative property. So it doesn't matter what order I do that multiplication in. Here C is a constant, and of course it's not multiplication, it's a dot product. But if you have a constant, a number that is multiplied by a dot product, you can move that anywhere within the dot product. You can move it out front, or you can multiply it through one of the vectors, doesn't matter. The fourth one is the only one that's not super self-explanatory. It's kind of weird. It's not a multiplication property that we would see very often. It says the dot product of any vector and itself is the same thing as the magnitude of that vector squared. Okay, so the dot product of any vector and itself is the same as its magnitude squared. So let me give you an example. Let's say I say vector v is xy, whatever that is, okay? And I'm going to do two things. I'm going to do v dot v, and I'm going to do the magnitude of v, and then I'm going to square it, okay? So if I do v dot v, remember we calculated dot product yesterday, we're multiplying the first components, multiplying the second components, and add them together. Just got to remember it's the same component, it's the same vector. So if I did the dot product here, I would do x times x, which would be x squared, plus y times y, which would be y squared. Okay, so that's what the dot product of that vector and itself is. If I wanted to calculate the magnitude of v, that's just our little Pythagorean theorem we've been practicing, right? Square root of x squared plus y squared. Well, this property says if I take that magnitude and square it, I'm going to be left with what I found for that dot product, which if I square a square root, we know that the square root is going to cancel. So I'm left with that x squared plus y squared, which is the same as the dot product of that vector and itself. So it's kind of like a mini little proof of that property. Okay. Questions on those? All right, let's do an example now. Okay, it says let v and w be two vectors in a plane that have magnitudes 20 and 12 respectively. The angle between them is 65 degrees. Find the magnitude of v plus 2w to the nearest 10. To the nearest 10 is going to exclude it. There's probably going to be a calculator used somewhere in here. All right, we are calculating the magnitude of v plus 2w. Okay, that's our ultimate goal. And so that means I need to find v plus 2w, and then I need to find the length of it. And that final number is going to be my answer. Here's the problem. I don't have v and w on their own, right? I know how long each of them are. I have their magnitudes, but I don't have them. And I have an angle between the two vectors, but I don't have angles for each individual vector. Like if I knew the direction angle of v and the direction angle of w, I could find the vectors with that information. But we don't have enough information. So we have to figure out another way to do this without actually finding the vectors themselves. So what we're going to use are all these dot product properties. Even though I don't need it, I'm going to calculate this squared first. And at the very end, I'll take the square root to undo it. Okay, but as soon as I put that squared there, I can use one of my properties. The property number 4 that we just talked about said the magnitude of any vector, which this is v plus 2w is that final vector, squared is the same as the dot product of that vector with itself. Okay, and now we're going to use all those dot product properties to simplify the right-hand side. Now, if you didn't know anything about vectors, you would think this is a foiling problem, right? 2 terms times 2 terms. That's pretty much what we're doing. We're using that distribution property, which is all foiling is, for dot products. So we're going to do my first terms, and we're just not multiplying, though. We're going to write v dot v. Those are my first terms, okay? My outside terms are 2w dot v. My inside terms are 2w dot v. And my last terms are 2w dot 2w. You can label those first, outside, inside, last. Okay. Another one of those properties that I'm going to use is, it was the one with the C. It says if I have a constant, which is 2 in all of these problems, I can put it anywhere I want. I'm going to move it to the front of each term just to separate it from the dot product. So it's going to be 2w dot v plus 2w dot v. And in the last one, if I move both 2's out front, it'll be 4w dot w. Okay, and then my middle terms are like terms. I can add them together. So v dot v plus 4w dot v plus 4w dot w. So that's as far as we can simplify that. Okay, so now we're going to find those 3 dot products. The first one is v dot v, and actually, let me do it in a different color. This is one of our properties. If I have a dot product of a vector and itself, what's it equal to? Magnitude of that vector squared. So I'm going to replace it. And I'm going to do the same thing for w at the end. I'm going to bring down that 4, but I'm going to replace it with the magnitude of w squared. And this is good because I know the magnitude of v and I know the magnitude of w. Okay? The only thing that I can't plug something in for yet is w dot v or v dot w, either way you want to think about it. We had 2 definitions yesterday to find the dot product. The first one was if we actually had the vectors, multiply the first components, multiply the second components, add them together. We can't do that. The second definition we had was that formula that was the angle between vectors. It said that the dot product is equal to both the magnitudes times the cosine of theta. Remember that from yesterday? Okay, so that's what I'm going to replace it with. I'm going to bring down the 4, but then that dot product is equal to the magnitude of each of them times the cosine of the angle between. And that's helpful because I was given the angle between. So now if you look up, everything that we're given can be plugged in somewhere here. So the magnitude of v is 20, and I'm going to square it. Plus 4 times the magnitude of w is 12, times the magnitude of v is 20, times cosine of the angle between is 65 degrees. Plus 4 times the magnitude of w is, what was that one, 12? Squared. And now you just type the whole thing in your calculator. All right, so 20 squared plus 4 times 12 times 20 cosine 65. 12 times 20 squared. I get 1381.71. Okay, remember, that is the magnitude of v plus 2w squared. I'm almost done. The question asked for just the magnitude of v plus 2w. So your last step is just take the square root of both sides. Take the square root of that number we just found. To the nearest tenth, it said 37.2 would be our answer. Okay. These ones are going to look very similar to the other ones in Math XL. But they're going to be tricky because it's going to be asking for a magnitude of vectors that you don't have. Okay, so that's how you know to use this procedure. Okay. Yes?
Wait, how do you even get to 65?
It was given to us. All right, any questions? Properties, dot products. All right, so other thing that we have not talked about, last, I guess, big topic of vectors is projection of a vector, projecting a vector onto another vector. Projecting a vector onto another vector is like pushing a vector straight down onto something else. Okay, so a nice way to think about this, and we don't have great lighting here, is like a shadow. Okay, imagine my arm is a vector and the floor is another vector. Wherever my shadow shows up is the projected vector, because that light is projecting my image onto the floor. Does that make sense? Okay, so that's kind of what you're seeing in this picture here. Okay, you can see that we've got this vector V and we've got a vector W, and if we have like a light directly above it, what we see here, this capital R, that's like the shadow, that's the projection onto that vector. Okay, so that's what we're going to be calculating. You won't need to really draw any of these pictures, I just kind of wanted to explain what it means. There are two formulas you need to know, and they're actually at the very bottom here. A lot of this is just kind of wordy. All right, so to calculate the actual vector, we're going to use this formula. Okay, so this is the vector projection of V onto W. And if you look at the formula, it's not bad. It's things we already know how to do. It's dot product divided by the magnitude of W. You can find that, square it, and you multiply it by vector W, whatever that is. Okay. That's the vector projection. Your answer to that will be a vector. The scalar projection is a really fancy way of just saying the length of that projection. So really all you need to write down is that last one. We take our projection and we calculate its magnitude, which again is not a new formula. We just use our little Pythagorean theorem steps to get that. What we end up is a vector projected onto another. Everybody got it? Okay, so let's do an example. Given vector V is 1, -2, and vector W is 2, 5, find the vector and scalar projections of V onto W. Okay, so again, formula will look like this. It is the dot product over the magnitude of W squared times vector W. Okay, and then once we find that, that'll be the vector projection. We'll find the length of it. That'll be the scalar projection. All right, so to the side, I'm going to calculate a couple of things I'm going to need in this formula, kind of like we did with that angle formula yesterday. I'm going to find the dot product first between the two vectors. And here they're given in that standard form. Remember, you might see with I's and J's, same sort of calculation. We're going to multiply the first components, multiply the second components, add them together. So 1 times 2 plus -2 times 5, I get the dot product is -8. The other thing I want to find is the magnitude of W, whatever you're projecting onto, okay? And that is not squared yet. We'll do that in a minute. That's just our Pythagorean theorem. So square root 2 squared and 5 squared give me rad 29. Okay. All right, so now in the vector formula, dot product -8. The magnitude of W is rad 29, and then I'm going to square it. So what's that going to be? Just 29. Times vector W, 2, 5. And then all we do if we have a constant next to a vector is just distribute it in. So your vector projection is -16/29 and -40/29. And that's the first part of your answer. Okay. So that's the shadow. That's vector V on top of vector W. Okay, then the scalar projection takes it one step further, and we say take that vector we just found, the negative 16/29, and the negative 40/29, and find the magnitude of it, find the length of it, which is just our little Pythagorean theorem. I'm not going to put my negatives in there. 16/29 squared and 40/29 squared. And then I'm just going to round to the nearest like tenth for this one. And I get, I'm going to go to a couple decimal places, 1.49 you get about. So that's the length of that vector. Okay. All right, just got one more problem. Then we're done. Okay, last bit is decomposition or decomposing a vector. Decomposing a vector means taking a vector and breaking it into two separate vectors that add to get to the original one. There's an infinite number of ways to do that. So when we decompose in a certain way. We decompose so that the two vectors we break it into, one is parallel to a given vector, and the other is perpendicular or orthogonal to a given vector. And how we do that is with actually our projection formula. Okay, so first of all, our goal here when we decompose is to take vector v, whatever it is, and break it up into v1 and v2. So your answer to these problems are two new vectors, v1 and v2. You need to have both. v1 is parallel to vector w, and it's actually just your projection formula. If I take my arm and I project it onto the floor, right, the shadow is parallel to the floor. What we're creating is a parallel vector when we do that projection. Okay, so that's why our formula doesn't have to change. Oh, and don't forget the little w. I didn't circle that there. Then v2 is going to be orthogonal. Remember, that means perpendicular, essentially, to vector w. And once you have v2, all you have to do is v take away v1, because you already have half of it. v1 and v2 add to vector v. Okay, so that's really like the only new part. So again, just an application of this dot product formula, different ways it can be used. Okay, and again, this is decomposing v with respect to w. And you can check your answers at the end of this one. You can check that v1 is parallel to w. We talked about how to do that yesterday. You can check that v2 is perpendicular to w. That was the quick one. If you remember, do the dot product. Make sure the dot product's 0. Okay. Everybody have what they need here? Or we need another minute? Okay. All right. Last problem of the day. Find the decomposition of vector v. So you're finding v1 and v2, where vector v is 5, 1, and we're going to decompose with respect to w, which is the vector 4, 4. I got a little muddled at the end, it looks like, but 4, 4. Okay. First thing I'm going to calculate is v1. v1 is the projection of vector v onto vector w. So again, I need the dot product, I need the magnitude of w squared, and then I need to multiply it through w. Maybe we can do this part in our head. Can you tell me what the dot product of v and w are going to be? 24 is correct. So 5 times 4 plus 1 times 4. The magnitude of w, let's just start with that. So that's our little Pythagorean theorem with w. So I would do 4 squared and 4 squared, which would give me 16 and 16. So rad 32. And then we square it, 32. Okay, times vector w, 4, 4. Now, if you reduce 24 over 32, what do you get? 3/4. We are just multiplying 3/4 times 4, 4. What is our vector v1? If I distribute 3/4 in. 3, 3. Okay. That's half of my answer. That's actually the hardest part to get. They're telling you V equals V1 plus V2. Vector V, we know, it's 5, 1. And V1 we just found, it's 3, 3. Your job is to find V2, whatever's there. Now, this is nice, pretty whole numbers, so you can probably do this in your head. Can you figure out what numbers are missing there that I need to add to 3, 3 to get 5, 1? 2 and -2. That's it, okay? If you didn't see that, you can take V minus V1 to get V2, okay? Or if there's weird fractions and decimals and things. So if I do 5, 1 minus 3, 3, 5 minus 3 is going to give me that 2, and then 1 minus 3 is going to give me that -2 that I'm looking for, okay? So that and that make up the 2 parts of your answer. If you want to check it, you can use the rules we used yesterday about parallel, perpendicular. 3, 3 will be parallel to W, and 2, -2 will be perpendicular or orthogonal to W. Okay, so like V2, if you take the dot product with W, you'll get a 0. You can see that one pretty quick. You're going to get an 8 and a -8. It's going to be 0. And then V1, if you take that and W, well, actually, can you guys imagine 3, 3 and 4, 4 going in the same direction? I mean, that you can almost kind of picture in your head because they're nice, pretty numbers. But you can calculate like the rise over run for both of them pretty quickly and see that that's the same. They're both going to have a slope of 1. Okay? That's it for vectors. That's all the vectors. We're done. Okay. So, your homework. 7, 4, that one due tonight?
Yeah.
Okay. And then 7, 4 night, 7, 5 is due Monday night. So those are going to be your 2 deadlines coming up. 7, 5 Monday. And tomorrow is a Math Excel workday. Yes. 7, 4 is due tonight. So, right, tonight?
Yeah.
Yeah? Okay. Keep second guessing myself, make it Friday, but it's tonight. Okay, so you guys have the rest of the period today. You can be working on your 7, 4 Math Excel. Tomorrow, then you can work on 7, 5 in class. You can also work on the circuit training. I feel like this is a very easy circuit training this week. If you have not been doing them, this would be a nice opportunity to start earning tickets for like your final exam coming up. I think it's a relatively quick one to do if you want to try it. And tomorrow, Math Excel workday, and then Monday, we're going to do an escape room with vectors, like the vector from Despicable Me will be around. So we will do the escape room, and if you escape, you get a ticket on Monday. So, and then Tuesday is your quiz over vectors. Okay? Questions for me? All right. I'll do cell phone lotto.